Okay, hi everyone. Welcome to the 8th session of MedAI. So today we will have Nandita to give a journal club and she will discuss several papers on self-supervised and contrastive learning in computer vision. Nandita is a PhD student in the Department of Electrical Engineering at Stanford University. She is advised by Daniel Rubin. She received her Bachelor in Technology in Electronics Engineering from the Indian Institute of Information Technology with the highest honors. She is broadly interested in developing machine learning methodology for medical applications. Her current research focuses on observational supervision and self-supervised learning for leveraging unlabelled medical data and out-of-distribution detection for reliable clinical deployment. So without further ado, let's welcome Nandita to give a journal club.
Thanks, C, for the introduction. So today we are trying out a different format where instead of presenting research, we are going to discuss a bunch of papers from the lens of a common perspective. So let me first share my screen. Can you see my screen okay?
Yes.
Okay, cool. So today we are going to talk about a recent framework called self-supervision and focusing mainly on contrastive learning within that. And I'll be presenting the papers from the vision community, so natural vision, which is probably most applicable to the medical imaging community in today's group. So before we get started on discussing the papers, let me give a brief overview of what self-supervised learning is. So self-supervised learning is a method to extract representations from data when you're not given any labels. So instead, you want to infer pseudo-labels from just the data itself, as well as certain augmentations and transformations that you do. So the goal is to learn representations that are invariant to these transformations. And so you retain only the semantic high-level content. So there are two types of doing self-supervised learning. So one is you do a transformation to a particular data set, and then you identify what transformation it is. So transformation prediction is the task. And the other is called entity discrimination, where you're given multiple augmented entities and you're trying to discriminate between the augmented versions. So let's dive a little deeper into these two types of tasks. So the more classical techniques belong to the transformation prediction category. So things like rotation prediction. So you arbitrarily rotate your input images into multiple directions and then try to predict which rotation orientation it is in. And there is another called colorization, where you try to color a certain image given a black and white version of it. And there's also this solving the jigsaw puzzle, where you split your image into multiple patches and then try to identify the relative positions back. But going on to entity discrimination. So as I said before, the goal is to identify if two entity samples represent the same high-level entity or not. And when I say entity, it can mean an instance. So every data point is treated as a separate entity, or it can mean a cluster. So different clusters are treated as different entities, or a complete class, and so on. So contrastive learning is a type of entity discrimination task, and it has typically involved Siamese network variant. And I need to mention that it's not really new, but it has gained a lot of traction within the last couple of years because of its recent success. So the framework of every contrastive learning approach follows this pattern almost. So given a set of images, you're trying to get at least two distortions or augmentations. And given these two views, as they are called, you pass them to a deep neural network, which acts as an encoder, and you extract representations from these two views. So because they are views of the same image, you want the representations to be the same in the representation space. So then you add a loss, which tries to get the similarity between these two representations and pass it back to the encoder. And some examples of distortions include cropping, black and white images, Gaussian blurring, and so on. But there is one problem in this technique. So if you just post this as the problem to a neural network, it leads to something called collapse, where the neural networks can just learn a trivial representation. So just the representations will just be a constant vector. And so when you backpropagate it, you're never going to learn anything new. So the main engineering challenge is to make sure that this collapse doesn't happen, and you want to start the networks to learn. So in today's talk, I'll be covering like the most popular and very recent contrastive learning techniques. So because there are almost 6 papers, I think I have a lot of content. So we may not finish exactly on time. So I'll try to record all the other ones as well so that people can view it later. But I'd like these to be interactive. So because I'll be presenting works from different papers, if you have any questions, feel free to just interrupt me and ask. So let's start talking about SimCLR first. So SimCLR stands for a simple contrastive learning representation framework. And it was actually just last year that it came out from Google. And it is a self-supervised learning technique, and it focuses on instance discrimination. So this means that every image is considered as a separate entity from every other image. So because it's a contrastive learning approach, it follows this paradigm where it tries to maximize the agreement between views of the same image, and it wants to minimize the agreement between views of different images. So there is this attraction and repulsion going on. So the unique selling point of SimCLR is that this was one of the first papers to actually prove that this contrastive learning technique is scalable and works in a large setting for current day purposes with deep learning networks. And it outlines a bunch of simple transformations that work really well in practice, such as random cropping and then color distortion, so on. And it also introduced this fully connected projection head, which I'll talk about in a few slides. It also introduced this large batch size requirement because of the negative samples. So the SimCLR architecture is pretty simple. So you start with different images, and then you take multiple views of the same image. And these two images are passed to the encoders to get the corresponding representations, which are then passed to this projection head. And there is this attraction and repulsion where you want to maximize agreement between views of the same image and minimize the agreement between views of different images. And this attraction and repulsion is actually handled by the loss function. So SimCLR uses the noise contrastive estimator loss.
Sorry, Nandita, I have just one quick question. Can you go back to the previous slide?
Sure, yeah.
So here the CNN models are different, or this is just one single CNN model just with architecture? You are showing it as a different model?
Yes, so it is a single model, so it has the same weight. So you just pass it. So in time, it's actually like the same model that you're passing sequentially, but you're unrolling it in the images.
Okay, so you are unrolling it per images, but you don't have really the CNN model trained for each category. No, so it's like one. Okay, yeah. Okay, thanks.
So the noise contrastive estimator loss is also has been around for quite a while, and it's very popular in metric learning purposes. So this loss is basically just a softmax loss, but taking pairs of images at a time. So let's say you have a batch of n samples, and you're for each image you're taking 2 views. So now you have 2 n images, and you treat each. So consider a particular image, and then treat every possible pair with it. So now you have 2 n pairs, and only one pair is going to be a positive pair, whereas all the other pairs are going to be negative pairs. So in the numerator, you have the exponential of the similarity between the positive pairs, and then you normalize it with the sum of the exponentials of all pairs. So this is going to be the foundation for many of the frameworks in the, that I'll be discussing today. So if you have any questions, feel free to ask right now. Okay. And in SimCLR, the similarity that they use is explicitly cosine similarity. And Z in this formula represents the actual representation from the encoder. So, oh, was there a question? Okay. So, so in this, because I'm comparing multiple papers together, I'm actually not going to compare the results, because all the 6 papers, they benchmark on the same benchmark datasets with ImageNet and try to classify the top 1 accuracy and the top 5 accuracy, as well as a bunch of downstream tasks. And what is interesting is that all the papers perform really well in all of these tasks. And most are within like 3 percentage points within each other. So that can be due to the ImageNet data statistics itself, or it can be due to certain implementations and so on. So instead, I'll be focusing on the different findings that we get from each of these approaches. So that's how we'll be contrasting each of the papers. So in SimCLR, they found that the augmentations, So in SimCLR, they use the following augmentations. So they use this thing called crop and resize, where they randomly crop a certain image and then resize it. They also flip it. They also do a color distortion. They do rotations. They just mask an image randomly and then apply Gaussian noise and blur and Sobel filtering. So what was interesting is that not all augmentations are equally useful or important. Particularly the color and the cropping seem to be the most useful augmentations for SimCLR. And you can see that some rotations actually add very little, and in some cases it's been known to actually be detrimental to the performance. So in SimCLR, we'll be focusing on just the crop and color for now. So one thing to note about this crop and color is it's a little non-intuitive, because you're trying to prove that one image and a random crop of that image are actually the same entity. And you can imagine in a medical setting where if you have a chest X-ray and you are interested in a particular lung nodule, say, and you crop a different portion of the chest X-ray and then say, okay, that is also supposed to represent the entire chest X-ray, which is probably wrong. But because natural images use, the characteristic of ImageNet is that every image actually has just one focus point, so the cropping works really well. And they have 2 kinds of cropping. So one is the global and the local view, and one is adjacent view, and both are equally performant. As I was talking about before, the projection head is also something that was introduced by SimCLR that actually boosted performance. So right after the representations from the encoder, they tried 3 variations. One is they directly feed the representations to the loss. The second is they pass it to a linear layer and then pass it to a loss. And the third is they pass it to a 2-layer non-linear module with a ReLU function. And they found that this non-linear module actually gives better gains. And from a higher level, this projection head is basically just changing the dimensionality of the representation that you get from the projection, from the encoder. And these papers typically use the ResNet backbone. So the dimensions are around 2048 or 1024. So when you want to get a lower dimension, the projection head is actually pretty useful. Okay, and some of the top findings that one of the key takeaways from the SimCLR paper is that bigger is better for pretty much everything. So if you have a high batch size, it's very good. And in fact, they found that 2048 is pretty much the ideal batch size for their experiments. They also varied the encoder networks. So moving to a wider ResNet actually helped in performance than using a narrower ResNet. And training for longer epochs also helped. And as you can imagine, so these large batch sizes require extensive TPU usage. So they used 128 TPU cores, and they used a batch size of 4096 for their reportings. So while this is like really great performance and one of the earliest ones to show contrastive learning success, it's a little harder to directly translate this into practice as a medical informatics researcher. The problem, the reason why you need such a large batch size is because you need enough negative samples to balance out the collapse that I talked about before. So that's the reason why they need really large batch sizes. So are there any questions before I move on to the next paper? Okay, so the next one I'll be talking about is MoCo version 2, which is stands for momentum contrast. And again, it's also a self-supervised learning technique, and it also performs the same instance discrimination task as I talked about before, and also has the same loss function where it wants to attract images of the same views of the same image and repel views of different images. So the unique selling point of MoCo is that it does not need large batch sizes. So instead, it uses this dynamic dictionary lookup where it's a first in, first out queue of encoded representations. And it introduced this momentum encoder for this particular task. And it's one of the most highly efficient, memory efficient frameworks out there. So just as we have discussed SimCLR before, the premise is pretty much the same. So you have an encoder, and then you pass in an image query through it. You get the representation out, and then you have a bunch of lookups in your dictionary, and then you have their encoded representations, and then you compare the similarity between each of these representations. So just to compare how an end-to-end approach like SimCLR versus a momentum contrast approach is that in SimCLR, the encoder is the same encoder like Imran asked before. So we pass all the images, all the views through the same encoder and compare pairwise losses. Whereas in momentum contrast, you do not actually pass gradients through this encoder. So you do backpropagation only for the query encoder, and for the key encoders, you just use a momentum update from the query encoder. And so because of this, your memory requirements for each batch is almost negligible. So the main principles of MoCo are, it's more of an engineering technique than a conceptual technique. So instead of using negative samples from a given batch, you accumulate negative samples across multiple batches and use a dynamic dictionary to design the contrastive loss. So the dictionary keys are defined on the fly using a set of data samples. And it's a first in, first out queue. So it's not a static dictionary, but instead, as soon as you get a mini batch, you enqueue it, and then you dequeue the oldest mini batch. And the keys are actually encoded using momentum update with the query encoder. So the momentum update is pretty interesting. So it uses the past query update to the current key update, and then updates it to the next key update. And because like the backprop is actually intractable when you have such a huge dictionary. The momentum contrast was required in the first place, and it has been shown to be very effective for this particular function. And the loss is again the same noise contrastive estimator loss, and you can see that the exponentials are pretty much the same. The only difference is that instead of taking the cosine similarity, they use the dot product as the similarity metric. And you might be a little confused with the key query terminology, but it essentially means that like query is the one that you are the sample that you're interested in, and the key is the ones from the dictionary. So one of the constraints in MoCo version 2 is that the dictionaries need to be large, because all the negative samples are coming from the dictionaries. So in order to avoid collapse, you want this to be pretty large. And you also want it to be consistent during training. So it's critical that you use the query encoder's momentum update and not use a separate architecture for it. And they did a comparison where they did like an end-to-end approach, so a SimCLR kind of approach, as well as a MoCo. And this memory bank is basically you just accumulate the dictionary and then do backprop across the dictionary as well. And as you can see, MoCo is pretty easy to scale across multiple negative samples in the dictionary, and it also performs pretty well compared to the other versions. And what was interesting is that the MoCo's framework is not independent, is actually quite independent from SimCLR's design choices. So you can use SimCLR's design choices to boost your performance in MoCo. So the multi-layer perceptron projection head that SimCLR introduced actually proved to help in boosting MoCo's performance as well. And again, using stronger data augmentations for between the keys and queries actually help performance. And this is a little more tractable, because the compute that they used was just 8 GPUs, so which is more reasonable in a research setting. And a batch size of 256 is pretty reasonable as well. So I think MoCo is actually one of the frameworks that you can use off the shelf without needing a very large amount of compute. Okay, so before I move on to the next paper, are there any questions about MoCo? Okay, so the next paper is actually something called Bootstrap Your Own Latent, and it's from DeepMind, and it was introduced only in December last year. So again, it's a self-supervised learning technique, except that it's no longer an instance discrimination task, but it's actually an instance prediction task. So I'll explain this in a few minutes. So instead of having one, so far we've been seeing only one encoder, which is being used for keys and queries or multiple views and so on. But in Bootstrap Your Own Latent, you're actually having 2 encoders that are different. So the unique selling point is that no negative samples are required. So because there is no requirement of negative samples, it means that you do not need such large batch sizes to prevent collapse. And what prevents collapse is actually the network architecture, which provides asymmetry. They also introduced this prediction head, which is required in the network architecture. I'll be talking about that next. So as you can see, the Bootstrap Your Own Latent architecture is also very similar to what we've seen so far. So you have an input images, and then you take 2 sets of views, and you pass it through encoders. And it's kind of important to notice that these 2 encoders are actually initialized with different weights. So they're not the same network, but then they are variants of the same network. So now you get 2 representations which are completely independent, and then you are projecting them onto the multi-layer perceptron projection head. And what BYOL introduced is that after the projection head, it just added one more thing called a prediction network, where the job of this block is just to predict what the target is going to be. And so the concept here is that backpropagation happens only across this online network, and the target network uses the same momentum contrast that we saw before, where these weights are updated based on momentum updates from the online network. So if there are any questions about this might be a lot to take in, but if there are any questions, you can let me know.
I have a question. Are these two networks, is their architecture the same, or do they have?
Yes, so both the encoders have the same architecture, but they are parameterized differently. So there is, so this theta and then this eta, I think they're very different.
So, and the views are, so there's no negative sample here. It's just two different views of the original image. Okay, I see.
Yeah, and because they are the same views, they're the views of the same image, all you're trying to do is attract these two, so there is no concept of repulsion from the others. And because the job of this network is just to attract these two, you can get away with just a simple L2 loss, so you don't need the contrastive learning loss anymore. So to summarize, the main principle of Bootstrap Your Own Latent is that you have two neural network two neural network pathways. One is called the online pathway and the other is called the target. They have the same architecture, but different parameterizations. And the way the target network's parameters are updated is that they are copied over from the online network with a lag using the momentum contrast. So you can see that the equation is practically the same as what we saw before with MoCo. And because there are no negative samples required, the loss is just an L2 loss. And because you have two views, you can always interchange the views, and so you get two terms for your loss. So you get symmetric losses. So it's pretty interesting to note that this is the first network which does not need any negative samples to prevent collapse. So it was like a pretty surprising thing that this even worked, but it worked really well and pretty much on par with SimCLR and MoCo. So there has been a lot of study on like what actually makes this Bootstrap Your Own Latent from collapsing. Like what is the thing that actually prevents it from happening? And there have been some spin-off studies where they found that they do a batch normalization, which has been shown to be essential for preventing collapse. A few other papers also studied this phenomenon and then found out that it's not, there's nothing special about a batch normalization, but some kind of group normalization needs to happen in order to prevent collapse. So for instance, if you take a BYOL variant and then just the vanilla one, it performs really well and it uses the batch normalization. If you just remove the batch normalization, the accuracy drops to practically 0. But instead, if you provide a modified initialization scheme, the performance shoots back again. And if you perform some kind of weight scaling as well as a group normalization, then you get a pretty equivalent performance. So the idea behind all of these batch norms, group norms, or modified initializations is to redistribute the weight values across the two networks. So this is actually the thing that prevents the two networks from collapsing. And one of the findings from BYOL compared to SimCLR was that it was more robust in performance to certain transformations. For instance, in SimCLR, if you remove the color transformation, the performance drops pretty drastically. Whereas in Bootstrap, your own latent, even if it's not dependent on a particular transformation per se. But on the other side of the coin, it means that it's less explainable based on transformations. So you can kind of assume that in the medical community, you want some interpretability about I'm performing a transformation A because I assume like if I transform this image, I want it to be the same. But if any transformation works well, then it's a little questionable. And I think the more important thing is it also is robust to smaller batch sizes compared to SimCLR. And so I think that's one of the key findings, that they do not need negative samples and it's robust to smaller batch sizes. But because this is also from the industry and they have a lot of compute, they have used 512 TPU cores, which is impossible to think about in an academic research setting. And they use the 4096 batch size throughout their computation, apart from the ablation studies. So as we move across these papers, it's kind of important to think about the practical usage case for each of these papers as well. Okay, so are there any questions before we move on to the next paper? So we are actually pretty good on time, so if there are any questions.
So, so the paper that you were just describing, it was only tested on the ImageNet, or they also tested on any other imaging data set? Because I imagine that this kind of transformation also depends a lot on the imaging and the class that you are mainly interested in, the groups that you are mainly interested in.
That's a great question. So what they do is they pre-train on ImageNet. So they perform all the training on just ImageNet, but they have evaluated it on a bunch of downstream tasks, and it performs really well on all the downstream tasks. So
did they show in the paper like any kind of effect or transformation based on defined data set, or it was consistent across all the data sets, especially the transformation graph that you were showing us before, that the accuracy, exactly. The accuracy drops for every transformation. So do they show the similar trend for every data set, or?
So the datasets that they have chosen are pretty standard. So they haven't chosen like a unique data set which may have different statistics. So for instance, ImageNet, CFAR, I think they also tried it on like a flowers data set and iNaturalist, but they all have certain common properties about the type of images. Like for instance, the images are always well cropped, and then the focus of the image is actually occupies almost the full frame and so on. So I think this is an active area of research, especially for the medical community, because there's a correlation between what type of augmentation you do with what downstream task you want. So that's actually one of the things that I'm focusing on in my research. So hopefully when I give my research talk one day, I can
Right. Okay, makes sense. Thank you.
Yeah, of course. Okay, so we can move on to the next paper, which is SwAV. So it's before I actually move on to discussing the details of this paper, it's pretty remarkable that all of this came only from like last year, and so all of these successes have happened within a span of months, and each of them is a variant of another, and then each new thing is coming up pretty recently. So SwAV is also a self-supervised learning technique, where the primary goal of SwAV is to swap assignments between views. So so far, whatever we have seen is an instance discrimination or an instance prediction approach, where they treat every instance as a unique entity. So you can imagine, so in that scenario, an image of a dog versus an image of of a different dog, they're actually not considered to be part of the same class, but they're considered a class by itself. SwAV is one of the only papers in the 6 that actually follows a clustering-based approach. So it tries to group images based on what cluster they belong to, rather than treating them independently. So in a way, you can think of clustering-based approaches as relaxing the task instead of the loss. So what I mean by that is in an instance-based discrimination, ideally you want to, given a particular image, every other image in the dataset needs to be a negative sample. But because that's computationally intractable, what you do is you take a large batch and then say, okay, every other image in that batch is a negative sample. So in that way, you're actually relaxing the loss a little bit. In the clustering-based approach, you're relaxing the task itself, because you're saying, instead of treating every other image to be a different negative sample for the task, I want to treat different clusters as different entities. So the typical drawbacks of such approaches are the performance issue, because to perform clustering during training, you need to do you need to make a full pass across the entire data set, which is computationally intractable. So what is unique about SwAV is that they do this online cluster assignment, and which is computationally tractable. And they introduced this multi-crop augmentation policy, which has been shown to be effective in all settings, not just SwAV. So moving on to the SwAV architecture. The first part is pretty similar to what we've seen before. So you have a bunch of images, you take multiple views, pass it to the same encoder, and then this part gets a little more tricky. So let me explain this a little in detail. So please feel free to ask questions, because this is a dense slide that I'll be walking over. So let's focus on a particular batch. So you have a batch of images of size, say, n cross n, and the number of images in this batch is b. And then you perform 2 augmentations, any of the augmentations, and then you get the 2 views of these images. So you still have b samples, each of n cross n size. And now you're passing it on to your encoder plus a projection head, which transforms each of these n cross n images into a single vector, so of dimension d. So these are the representations that you get from the encoder. So what SwAV is doing is that the online clustering is a very unique feature. It's what it's saying is that I will learn a set of k vectors. So this prototype matrix is a learnable matrix, so it's randomly initialized for now, where each of the columns represent the center of each of the clusters. So, so from the mathematical point of view, this is just a matrix with the correct dimensions that you can multiply with your representations. So when you multiply this dimension, the representation that you get from your encoder with this prototype matrix, you actually get a score which has k different classes. So, and once you have k different scores, you can now use your favorite probability distribution transformer. So such as, like, for in this case, they use 2 different kinds of techniques to transform a raw score to a corresponding probability. So the first one is something that we're all familiar with. So they just use the softmax to get the corresponding probability. The other thing, which is a little more complicated to understand, but it's actually very easy to implement in practice, is called the sync-hon. So I'll talk a little bit more about this in the next few slides, but you can think of this as 2 different ways of getting probability distributions from a raw score. So, so given that you have 2 different probability distributions for a particular batch of images, and then you have 2 different views, so you basically have 4 probability distributions. And that's where the swapping comes from. So what they want to do is they want to minimize the cross entropy between P1 and Q2. So they're swapping the probability distribution across the different views. So you minimize the cross entropy between P1 and Q2 and P2 and Q1. So that's essentially the final.
Sorry, I have a question here. So sure. Is the K the number of classes in the data set?
It's not the number of classes. It can, so K is the number of clusters that you are trying to cluster into.
So it's like is it like a hyperparameter that you can?
Yes. Right? So for instance, for ImageNet, which has 1,000 classes, they chose K to be 3,000. So the number of classes can be much less than the number of clusters, vice versa. They did an ablation study also, which I'll talk about, but that's a good question. That's not a principled way of getting K for now. It's an arbitrary parameter.
Okay.
Okay, so so just to recap, you have a particular batch of images with two different views, and each of these views gives you two probability distributions, and then you swap the probability distributions and minimize the cross entropy between the swapped predictions. So the cross entropy loss is just minimized between Q1 and P2 and Q2 and P1. So the terminology that they use for Q2 is the intermediate codes, and Q1 and Q2 is intermediate codes, and we know that P1 and P2 are basically the softmax values already. And the things that are learned via backpropagation are the encoder parameters themselves, as well as the matrix C. So that is also part of the backpropagation. So this is a different type of clustering where you're not doing a hard cluster. Instead, you're treating it as a probability distribution and doing a softer clustering. So what you do is you generate a matrix C that allocates different image representations into K different clusters. So what the matrix C is doing is essentially transforming or projecting a D-dimensional vector into a K-dimensional vector. And I'll skip over this part a little bit because in the interest of time. But if you are interested in learning about how exactly do we get this other distribution called synchron, like how do we get a probability distribution from the K-ROS course? They treat it as an optimal transport problem, and the way to solve this optimal transport problem is using the synchron NOP algorithm, which gives you two marginal probability distributions. So I'll just briefly give an intro about this one, but I think it's a little more complex than what is required to just implement SwAV in practice. So so given this ROS course, so when you multiply the prototype matrix with your representations, this synchron NOP algorithm tries to learn two diagonal matrices U and V iteratively, such that when you multiply all of them together, you get a matrix which is doubly stochastic. So it means that the rows and the columns all sum to 1, so which is perfect for a probability distribution. So one thing to note is that this works only if it works well when B is much larger than K. So you want the number of or you want the batch size to be much larger than K. So this means that if you have a K of 3,000, then you want a batch size more than 3,000, which becomes practically intractable. So instead, what they do is in such a scenario where the batch size is actually less than K, then they use the momentum contrast approach that we've talked about before, and they just accumulate the negative samples across multiple batches. So moving on to the other contribution from SwAV, which is the multi-crop. This is conceptually very simple, where instead of just taking two different crops randomly, they take multiple crops. So for instance, they call something a global view if it's a larger crop, and then a local view if it's a smaller crop. And then instead of having just two augmentations, you can imagine you have M such parallel networks, and then you compute the loss across all of them. So that's essentially multi-crop. And they found that it actually adds significant boost in performance, not just for SwAV, but they tried it across many other self-supervision methods, and it's boosting performance across all of them as well. So coming to the takeaways from SwAV, it's the performance is really good, very close to supervised baselines. They found that so because this K is a hyperparameter that we don't have a principled way of studying, they did an ablation study, and they found that it has less impact on performance as long as you have enough. So what is enough is a little questionable, but like they found that beyond 3,000, it didn't really help, but if it's less than 3,000, it hurt performance for ImageNet. So that's something to consider. And they used 64 GPUs with a batch size of 256, which again is reasonable, but not very easy to work with in an academic setting. So that's something to keep in mind as well. And yeah, so and as with all the other papers, they also did a lot of studies on downstream tasks and then performance on ImageNet and then other data sets, and then had pretty good performance across all of them. So, okay, so I think we have 10 more minutes, so I'll try to go over DINO, and we'll see how much time we have left for going over Barlow Twins. But if there are any questions, feel free to ask them. Okay, so DINO is a recent, like it's very recent, it just came out in iClear, and it again is a self-supervised learning technique, and it uses self-distillation with no labels. So the cool thing about DINO is that they use, so all the papers so far have been using a ResNet backbone. So DINO is the paper that moved from like ResNet-based encoders to a vision transformer, which is supposedly does semantic segmentation directly. So the USP is that the attention maps that they produce are actually like pretty amazing. So you can directly just the attention maps extracted from the last layer does the segmentation really well. And the relation between a vision transformer and self-supervised learning is explored for the first time using DINO. So before we actually go on to the concept behind DINO, I think it's kind of pretty cool to see the semantic segmentations that the attention maps produce. So you can see that the segmentation is pretty cool even without, so this is all done in a self-supervised manner, so that means no labels have been given. And so to understand what suddenly changed, like why is this performing so well, it's important to know what a vision transformer is. So instead of a convolutional architecture like ResNet, what vision transformer does is that it divides up an image into multiple patches and then projects it on to an embedding layer where both the patch representation as well as the position representations are given. And then you feed into a transformer, which has the same architecture as the ones used in natural language processing. which are then projected to a multi-layer perceptron head, and you just learn and after that you can basically perform classification. And the number of patches or the patch size for each of these images are usually around 8 or 16. DINO specifically uses 8 and 16 for their performance metrics. And just to see this in a more interactive setting, you can see that the position as well as the image encoding are given to the transformer. Which then projects it onto this MLP head, and the classification is performed on this token, that this extra class learnable embedding, so that helps you perform the classification. So moving on to the architecture of DINO itself. So the encoder is just one part of it. So the encoder is vision transformer, but the architecture of DINO is again very similar. So if you remember Bootstrap your own latent, it follows the same setting as that. It has given a particular image, you take two views across it, and you call one as the student network and one the teacher network. And as before, across the student network, you perform backpropagation, whereas in teacher network, you do not perform backpropagation. And like with Bootstrap your own latent, these are two different initializations. So they are the same architecture, but they're actually different parameters. And again, the way you get the update for the teacher network is via this exponential moving average from the student. So the new thing that has been done in DINO is that they added a softmax to the representations instead of just having it in the representation space. And because they've moved to a softmax, it means that they have to compare the probability distributions between the two. So which means that the loss is no longer just an L2 loss, but rather a cross-entropy loss. And the third thing, which I'll talk about in a couple of slides, is this centering aspect of it, which prevents DINO from collapsing. So the loss function, again, as I mentioned before, is just the cross-entropy loss. So previously in Bootstrap your own latent, they produced two representations of the same image, which they wanted to make identical. But now they have converted the representations into probability distributions using softmax. And so to minimize the cross entropy between them, you just use the cross entropy loss. And so the main principle to summarize is that they have the exact same architecture as Bootstrap your own latent, along with the exponential moving average update rule. And the encoder is also a vision transformer. They also tried it on fun nets and proved that it works really well. But it's interesting to see that vision transformer actually provides pretty good performance right off the shelf. And one thing that vision transformer does not require is any sort of batch normalizations. So previously, when the debate was going on between whether Bootstrap your own latents wins were because of batch normalizations to prevent collapse, we know for sure that that's not the cause of preventing collapse. So what actually prevents collapse from happening in DINO? That is because of the centering that I talked about before. So they perform the centering as well as the sharpening between two images, centering and sharpening of the momentum feature. And they do these two techniques to prevent out collapse. And so centering actually says that it's a very simple concept. It's just adding a bias term to the teacher, and you take the mean across the batch and then just subtract it from the teacher layer. And this encourages a uniform distribution. Whereas sharpening is automatically performed by the softmax because you add a temperature to it. So when you lower the temperature, it actually prevents it from moving to a uniform distribution. So this contrast in techniques here is actually what prevents collapse from happening. And again, they use the multi-crop techniques from SwAV with the same setting and see that it reduces performance quite a bit. And some additional findings that they saw were that the teacher network actually outperforms the student. So it's more useful to take representations from the teacher rather than the student. And this ablation study is pretty cool, where they analyze the effect of sharpening versus centering, and then prove that this phenomenon is what prevents the collapse from happening. Okay, so I think the takeaways are vision transformer plus self-supervision works really well with downstream tasks without any fine-tuning, and it's pretty robust to batch sizes. You can see between 128 and 1024, you do not have too much drop in performance. And the patch size actually is pretty important, where an 8x8 performs much better than a 16x16, but the throughput drastically reduces if that's the case. And they did a set of ablation studies where they showed that the momentum is essential for performance, and cross entropy loss as well as the multi-crop boost performance. So yeah, and the coolest thing about DINO is that it just requires two 8 GB GPU servers. So that's two 8 GPU servers. So that's pretty tractable in an academic setting. And yeah, I think maybe this might be a good time to stop. Are there any questions? So, okay, if there aren't any other questions, maybe. Oh,
okay, if there is no other question, let's thank Nandita for this amazing talk. A very nice talk summarizing this exciting field of self-supervised and contrastive learning in computer vision. And yeah, so if you have questions later, feel free to post them under our YouTube video or in the Google form on our website. All right, if not, let's thank Nandita again and see you next week.
Thank you, Nandita. It was very interesting talk.
thank you. Yeah.
Bye.
Yes.
Thanks.
Thanks.